So that's it for our first lecture in machine learning course, which was about linear regression. So here we taught you several things. So for example, like we taught you that in supervised machine learning, there's always a data set which is sort of n data points, where your input data samples like xj is a k-dimensional vector and y is a scalar. And then we also taught you that there is some feature representation which we call basis function or feature function, which you use to compute the nonlinear representation of the input variables xj. So it maps the some real k vector to some real n-dimensional vector, which may be a nonlinear representation of the input data samples xj. Then we also taught you the linear models. That is, in this lecture, we considered that our function f is a linear function of its input. That is, it's parameterized by some learnable parameter w, and we compute the output as w transpose times phi of xj. And we also showed you like why this choice of directly feeding in the input data points, it can be a poor choice. For example, it may not be able to capture the semantics of any data set that is non-linear in nature, that is where the output is a non-linear function of your input data point. So in that case, this representation phi is very useful because even while we are selecting the linear models, we can capture the non-linear semantics of the data by just having a correct representation, or you can say right choice of representation. We also considered the L2 norm cost function to train our algorithm to actually compute the learnable parameter w. So we computed the optimal solution for this kind of functional mapping from input data points xj to the values yj using closed form solution and the gradient descent solution. So this is so this lecture is about was about linear regression and machine learning. And you may ask that how is all this relevant in 2019, where companies are investing like billions of dollars in deep learning, autonomous driving, robotics, and you can go on the internet and you can check fancy research paper with their very fancy mathematics in various like deep learning papers basically. So you may ask, how does this linear regression or typical like classical machine learning fit into the current deep learning trend basically? So one of the very basic things is that, if you remember, we instead of learning the functional mapping on this input data points xj, we learned it instead on some nonlinear representation of the input data points phi, right? So let's suppose that instead of doing linear regression, you are training a deep learning system to do some regression. So how do things change over there, right? So we learned that we have a function with some learnable parameter w, which takes some input and it constructs the output is computed as some linear function of its input, right? And in lecture, we showed two different scenarios. One where you are using just the input data points to compute the output. And in another case, we computed a nonlinear, a basis function, feature function, which can be a nonlinear representation of your input data points. So in second case, we selected phi of xj, which then becomes, right. So instead of doing this, we told you that this is a much better choice, right? And now you may ask, okay, if I want to do deep learning on some data, how is this lecture relevant, right? Now in deep learning, what happens, right? Okay, let's consider linear regression. What actually happened, right? So let's construct a black box. Let's call it regression. So what happened in this lecture, right? We selected some input data point, xj, and instead of directly feeding it to our model, we had an intermediate layer. Phi. So x goes as an input to this box phi, And this box outputs some representation, perhaps a nonlinear representation of the input data points, and it feeds in to the regression black box, which has its cost function, right, which is an L2 norm, that is, L2 norm squared over all the data set, which means that it is squared each of the, so let's represent for each of the data points, the error was EJ. So just squared those errors and it added all the errors. Right. So this is what the cost function. So you have this cost function. I'll just erase this to keep things simpler. And then basically it had another ingredient, which is a learning algorithm. So in our case, we consider a closed form solution, right? But later on in machine learning course, you will learn that closed form solutions can only be computed for linear regression, cannot be computed for any other sort of like class of functions. So you'll learn this later in the course. So we had another ingredient, a learning algorithm. Which was nothing but a gradient descent, or a stochastic gradient descent, or perhaps omni gradient descent. So we'll just call it stochastic gradient descent. Or simple SGD. Right. So just to make things simpler again, we can just write this learning function as SGD. So after combining all these modules, we pass this input data point. It goes to the second black box. That black box outputs something and goes to the third black box, which has its own, let's say, parameters of this black box, which is a loss function plus a learning algorithm. And after doing all of this, over the dataset D, right, what we get as an output is optimal solution W star, the learned parameters. Right. So this lecture is not about deep learning, and deep learning is a different topic on its own. So here we are going to construct a very crude example of deep learning as to how this entire learning process, or everything that you have learned in this course, makes sense for deep learning model. Let's suppose if you want to directly try a deep learning model using some library, which can be, there are like n number of libraries available nowadays, so you can use any of those libraries. So how does everything that you learn in this course fits into deep learning, right? So in deep learning, what happens is that here, let's suppose we have a data set where you have cat, dog, a tiger, a lion, a cow, and so on. Let's suppose you have 10 different animals, right, in images. And now we are passing you perhaps 1 million images, right, for you to train your algorithm, right, on that data set. Now, let's suppose you train your algorithm, right, using regression. The first thing that you'll have to do is select a feature function that takes your regular image as an input and it maps it to some vector, right? So you have to construct a file, right? And this is one of the most difficult parts, of problem in pattern recognition, right? So here we are trying to sort of recognize a pattern image to say whether this image belongs to cat or a dog or a tiger or a lion or a cow, right? For autonomous driving, these can be obstacles. For example, it can be pedestrian, it can be a car, it can be a regular block on the road, right? So you want to classify the obstacles according to the class, right? The first thing you have to do is to construct a very good representation function, a basis function or a feature function that takes your image and makes some meaning out of it, right? And then you can give phi of I to your algorithm, and perhaps you can perform regression on it, right? But this will give you, like, it's very hard to come up with a phi that allows you to do this, right? In a right fashion, right? So this is where deep learning comes in, right? So with deep learning, you don't need phi, right? Deep learning will automatically construct this feature presentation for you. So let's make another black box. DL, or deep learning for short, right? So here you will directly pass your input image or the training example XJ, right? You'll have to supply a loss function again, right? And you have to supply a learning algorithm to a deep learning model that you're constructing. So perhaps here you can select the stochastic gradient descent. So for regression, the L2 square loss function works well. But let's suppose for deep learning, you select another loss function. Perhaps if your goal is to rank the confidence of the learning algorithm pertaining to each of the class, then perhaps you can perform regression on those confidence scores, right? And then this becomes again your regression problem. So here again you can select your L2 loss function. Right? And again, so you can see the only component that was reduced when you went from linear regression to a deep learning model for regression is that you didn't have to construct this file. Deep learning system does it automatically for you, right? So deep learning system will give you optimal parameters. So here we said that it's a linear regression because the function f was linear both in its input and also the variable w, right? Since this function is linear in w, we call it a linear regression, right? What happens in deep learning is that this representation, like this may not be a linear function of its parameters, right? So here the deep learning will automatically construct a good phi for you. And it will output some optimal parameter, a matrix, like it can be a very high dimensional matrix of optimal parameters W. And now you can use these parameters, right? Learn parameters for deep learning, and you can pass a new image X hat and perhaps get its confidence score on all these different classes, right? So all the things, the loss function, the learning function, and the input, the feature condition, everything is relevant. It's only that the deep learning model gives you the optimal parameters. Along with that, it also gives you very good representation. The deep learning model itself builds some highly sort of non-linear, high-dimensional representation of your input data points X. So whatever theory you're going to learn in this course, be it pertaining to optimization, the learning algorithms like stochastic gradient descent, or different kinds of loss functions when we discuss different kinds of machine learning algorithms, all of this will help you to construct your own loss functions, to construct your own learning algorithms, and it will help you to select the deep learning model that is best suitable for the problem that you're solving, right? So you can combine the knowledge from this course to apply it to some to construct some deep learning model to solve a real world problem in the area of computer vision, pattern recognition, autonomous driving, or some control problem. So that's it in the first lecture of machine learning, which was about linear regression. And after this lecture, you'll get assignments, which will include both mathematical as well as programming questions. And the programming questions will be solved in Python. And you'll be learning new libraries as well. To learn more about the stochastic gradient descent or the gradient descent algorithm, you can follow TA lectures, who will also explain you how to submit the assignments.